The transition operators of a time-homogeneous Markov process form a semigroup. That's what the Chapman-Komogorov equations say in the time-homogeneous case. That is, they have the form e to the ta, roughly speaking, for some operator a. But when does that operator exist, and what does it mean when it does? Well, in the next several lectures, we're going to explore these questions, especially in the case of a countable discrete state space and continuous time process. As a reminder, a Markov transition semigroup has a generator called A if this limit exists. That is, the limit as t goes to 0 from above of qtf minus f over t for any bounded measurable function f on the state space. That's the derivative of the transition operator applied to f at time 0, or more precisely, the right derivative, since the semigroup isn't even necessarily defined for t less than 0. If the semigroup has the form qt equals e to the ta for some operator a, where this is given meaning, for example, by a power series, if that makes sense, then this procedure will recover the operator a. We want to figure out when it will be true that this limit exists, and if so, can we write our semigroup in this form? This is a delicate question, and we're going to be answering it in the most agreeable case in the next lectures, where there's enough regularity around to make this make perfect sense with few subtleties. Now, let's start by stating the obvious. If this derivative exists, if qt is going to be, in an appropriate sense, differentiable at 0, then it has to be continuous at 0. But qt is a family of operators. It is a function from the positive real line into the space of operators on the space of bounded measurable functions on our state space. There are a zillion different topologies we could use on that space in order to measure the continuity of this operator. So we're going to focus, for now, on the strongest possible topology that we would want to use there, and that, we'll see, will give us the nicest possible results. And that is the operator norm topology. But I want to point out that everything we're going to say about operator norm continuity here is usually too strong for Markov transition semigroups associated, for example, to continuous state spaces. For example, none of this would apply to Brownian motion. Let's start out fairly generally. Suppose we're given a normed space. This is going to be an example of a normed space. So for us, we'll be primarily concerned with the case where this is the space of bounded measurable functions. And the norm is the supremum norm that we've been working with. Now, if we have a linear operator on that normed vector space, we can compute its operator norm. And that's defined to be this, the maximum distortion of that operator. That is, we apply the operator to any function. Let's make it non-zero, since we know what a linear operator does to the zero function, and see what the norm in this normed space does in relation to the norm of the original function. How much does this distort the norm of the function under the operation A? Now, one thing we can do right away is to bring the scalar 1 over the norm of f, which is a positive real number, inside the norm here, since norms have that property. The norm of alpha times a is going to be alpha times the norm of a for any positive real number. So if we consider this function here, f divided by its norm, that's going to be a generic normalized function, which we usually indicate with a hat. So we can alternatively write this as the supremum over all elements of our normed space with norm 1 of the norm of that element under A. Now, it's perfectly possible for this ratio to have no upper bound as we consider all possible functions of norm 1. And so we would say such an operator is unbounded. If, on the other hand, this ratio has a finite supremum, then we call the operator bounded, and this is its operator norm. Now, let's note what bounded really means here. Using the linearity, we note that if I have two elements, f and g, of the normed space, consider the difference, af minus ag, by linearity of a, that's a applied to f minus g. And if this ratio here is bounded by this finite constant, then this will be less than or equal to that constant times the norm of f minus g. In other words, to say that a is bounded is to say that it is Lipschitz continuous, with Lipschitz norm equal to this. Hidden in that terminology is the fact that on the set of bounded operators, this is actually a norm in its own right. And that's an easy exercise that I'll leave you to work out on a napkin in your spare time. One feature of that norm that is going to be important for us is that not only is it subadditive, as norms have to be to satisfy the triangle inequality, it is also submultiplicative. The space of bounded operators is an algebra. We can not only add two operators together, but we can multiply them, that is, compose them. If a and b are two linear operators, then it turns out that if both of them are bounded, their composition is also bounded. That's not surprising. A composition of two Lipschitz functions is a Lipschitz function. And moreover, the operator norm of the composition in either order is less than or equal to the product of the operator norms. Let's prove that. We'll revert right to the definition. We take any non-zero element of the normed space, f, and take this ratio. Well, first of all, if f is in the null space of the operator b, then we just get 0 here. Otherwise, if bf is not equal to 0, then we can do the following trick and write this ratio as abf norm divided by the norm of bf, which will be a positive number if f is not in the null space of b, times the ratio norm of bf divided by the norm of f. Well, that tells us, thanks to this 0 here being something that is pretty much never the supremum, that in this supremum here, we may as well restrict to those functions not only that are non-zero, but are not in the null space of b. Of course, 0 is in the null space of v, so this is actually a helpful restriction here. Now, this is a supremum of a product of two positive functions of f. And a supremum of a product is less than or equal to the product of the suprema. Now we have two elements here, each of which is bounded by the appropriate thing to give us the product of operator norms. In this case here, we're looking at basically the definition of the operator norm of A, except we're restricting to functions that are in the range of B instead of all non-zero functions. Well, that's okay, because if we expand this supremum to be taken over all functions G instead of just those functions that are in the range of B, we get that this is less than or equal to the supremum over G not equal to 0 of the ratio of the norm of AG to the norm of G, and that's the operator norm of A. And here, we know that if f is 0, then bf is 0, which means that the set of functions for which bf is non-zero is a subset of the set of non-zero functions, and so this term is less than or equal to the supremum over the larger set of all non-zero functions of the ratio of the norm of bf to the norm of f, and that's the operator norm of B. And that shows this property, as we hoped. Now we can immediately do induction on this formula to see that if I take any finite collection of operators a1 through an, then their composition a1 composed with a2 composed with up to an will have operator norm less than or equal to the product of all of their operator norms. In particular, if we take all of those operators equal, then we see that the nth power of any bounded operator is bounded, and its operator norm is less than or equal to the nth power of the operator norm of the original operator. And from there, we can also see that we can take the exponential of a bounded operator and get a bounded operator. We're defining the exponential here of an operator, including this extra t, since we're going to need that around later, by the power series. Now, here we're taking a power series not in the real line or the complex plane, but a power series in the algebra of bounded operators. But that's just some normed space. We can take power series in normed spaces, and they'll converge in the usual ways if we can prove that there is a finite radius of convergence. So that's what we're going to do here. We can use this result up here to show that this power series has an infinite radius of convergence, if you like, in the real number t. And in fact, that the power series here converges to a new operator whose operator norm is less than or equal to this, the exponential of t times the operator norm of the original operator. So all of that is fairly elementary. Let me just note that for the last step, what we're really using is the Weierstrass M test, which says that all we need to do is control the tail of this series. And in order to do that, we just need to show that the sum of the terms in the series is finite. Then we'll get convergence of the series. Now, to be clear, in order to really make that work, we need the normed space in question to be a Banach space, a complete normed space. Well, in fact, the set of bounded operators on any normed space is a complete normed space in the operator norm. Again, this is a fact that I'm going to leave to your outside reading. It wouldn't be hard to prove, but I'm not going to take the time to prove it here. So, having that assumption under our belt, we just have to check that this holds true, because then we will see that this converges to some finite element of the Banach space in question. Well, that's just a matter of fiddling with power series. If we take the sum here of the operator norms of those terms, first, operator norm is a norm, so we can pull this constant out with an absolute value sign. And now we'll use the induction step in the first statement of the proof to move this n outside. And now that is exactly the power series expansion of e to the absolute value of t times this constant, the operator norm. If a is a bounded operator, then that operator norm is finite, and so this exponential is finite, which shows by the Weierstrass M test that we do have an element here of the bounded operators, which we'll call the exponential of ta. Now that might look pretty abstract, but let's specialize it to a case that is going to be most relevant to us. Let's suppose that we're talking about a Markov process with a countable discrete state space. That means that the state space is countable and the sigma field is the field of all subsets. One way to produce bounded operators on such a space of bounded measurable functions on a countable set is through matrices. That is, a function, which I'll call little case a, of two state space variables. If we have such a function, then we can nominally define an operator on bounded functions here. AF is going to be the new function which takes at each state I the value through matrix multiplication, summing over all states j, aij times f at j. Now that of course makes perfect sense if you have a finite state space no matter what, but if the state space is infinite, we're going to need some conditions on this matrix A in order for this sum to converge and define a bounded operator A. Now, since our only assumption is that f is a bounded function here, all we can really say is that this is less than or equal to some constant. And so in order for this sum to be convergent for all such functions, we'd better have that this series as a function of j is absolutely summable. That is, we better have that for each fixed I, aij is a little L1 sequence. Its absolute values are summable. So that will tell us that this gives a finite answer for each I, but we don't just want a finite answer for each I, we want a bounded function to come out. This is supposed to be an operator on the space of bounded functions. And so the number we get for each I had better produce a new function of I which is bounded. So that means that this sum should be finite and uniformly bounded in I. In other words, let's define the infinity norm of such a matrix to be the supremum over I of the sum over J of the absolute value of Aij. If we take a matrix for which this is a finite quantity, then we can quickly compute that this new function that's defined here is bounded, and in fact is bounded as follows. This is the supremum over I of the absolute value of the sum over J of Aij times f at j by the triangle inequality for countable sums. That's less than or equal to the supremum over I of the sum over J of the absolute value of Aij times f at j. Well, f is a bounded function, so this is for all j less than or equal to the supremum norm of f. And once we pull out that constant, what's left here is exactly what we defined to be this constant here. So this whole thing is less than or equal to that infinity norm of the matrix times the sup norm of f. That is really why we've used the same notation here for the matrix as we did for the bounded function. Now that is a finite number, and therefore this is a bounded function. Actually, what we've shown from this calculation is that the operator A is a bounded operator, and its operator norm is less than or equal to this quantity here, because dividing through by f, we get exactly this is less than or equal to that. So that is an upper bound for that ratio. Well, in fact, it's not just an upper bound, it's the least upper bound. It is the supremum. It is the operator norm of this operator A that we've so defined. That's going to be important, and so let's prove that right now. If we have a countable state space and a matrix over that state space, if it has finite infinity norm, then the operator so defined by matrix multiplication is a bounded linear operator on the bounded functions on the state space, and its operator norm is equal to that infinity norm of the matrix. So the first half of that we showed on the last slide. That is, we showed we have this bound here, and that exactly means that this is an upper bound for the operator norm of A. So for the converse, we need to show the reverse direction, that the operator norm of A is greater than or equal to this quantity. And to that effect, let's, for each I in the state space, consider the following bounded function fi. It's going to be determined by the matrix A like this. We define the function fi at j to be the signum of Aij. Except I've put a star there. As we'll see in a moment, it's a slight modification. Now remember, for a real number a, the signum is 1, -1, or 0, depending whether a is positive, negative, or 0. We can extend that to complex numbers just as well. We define it to be the complex conjugate of a divided by the modulus of a, if a is non-zero. Now, this is defined in such a way that if I multiply this number by a, what I get is the modulus of a. That's what the signum means. There's the question of how to define it if it's 0, and in this case, and that's what the star indicates, instead of making it equal to 0 when a is 0, I'm going to make it equal to 1 there. So this always gives me a complex number of modulus 1. And the reason I want to do that is because it therefore follows that this fi always has infinity norm equal to 1. In fact, the modulus of that function, whether you take the supremum or not, is equal to 1, always. Now, if I apply the operator a, whose matrix is little a, to the function fi, and I evaluate that function at I, what I get is this sum here by matrix multiplication. But because of the way we've defined this, when I multiply a by this, I just get the modulus of a. And that's still true if a is 0, because if a is 0, the modulus of 0 times 1 is 0. So this gives me the sum over j of the modulus of aij. And that means that this is also the absolute value of that, since this is a non-negative quantity. Well, therefore, if I take the supremum over all of these values here, it's going to be bigger than or equal to this instance. And so the supremum of AFI over all j's is greater than or equal to that quantity there. But that supremum is equal to the norm of AF, and it's also equal to the norm of AF divided by the norm of F, because the norm of F is 1. So what we've shown is that taking the supremum over all F's, that the operator norm of A is greater than or equal to that sum, and that's true for all I. Since it's greater than or equal to that sum for each and every I, it's also greater than or equal to the supremum over I, which is the infinity norm of the matrix A. And that's what we wanted to show, that the operator norm is not only less than or equal to that, it's also greater than or equal to that. So the infinity norm of the matrix is the operator norm of its associated operator. Now let me give you an important word of caution here. What we've shown is that if A is a bounded operator on the space of bounded functions that is given by a matrix, then its operator norm is equal to this quantity, this infinity norm of the matrix. That doesn't mean that every bounded operator on the space of bounded functions has a matrix. In fact, that is emphatically false. And that's going to give us some trouble later, which we'll be able to work around if we're careful. This might seem a little counterintuitive because you're used to linear algebra, where of course every linear transformation has a matrix. Well, in finite dimensions, that is, if our state space is finite, all of this is going to be a lot easier. If we have a countably infinite state space, there will be bounded operators on the space of bounded functions that don't have matrices. Now, it might feel like we've just delved into a new course on functional analysis instead of probability theory and Markov processes. So let's get back to reality here and point out what all of this has to do with Markov transition kernels. I'm now going to state a theorem that we're going to prove next time, which showcases where these tools that we've just developed come into play. If Qt is a family of Markov transition operators on some state space, SB, if we assume that as a function of t, Qt is operator norm continuous at 0. That is, if as t goes to 0, Qt converges an operator norm to the identity operator, then things are super nice. Remember, in the last lectures, we saw examples of Markov transition semigroups that were discontinuous at 0. We could just take Qt to be a fixed matrix, all of whose rows are equal. Any such degenerate stochastic matrix itself forms a transition semigroup, but it's definitely not continuous in any sense at 0. And so all hell breaks loose in that case. In order to have a generator, we need continuity at 0, and here we're going to assume the best possible continuity at 0, operator norm continuity. In that case, not only is Qt continuous at 0 in operator norm, it's continuous on the whole positive real line in operator norm. And it's differentiable on the whole positive real line in operator norm. To be precise, the generator, which is this derivative at 0, and that's defined in terms of the operator norm, exists. That's what we wanted to show. Remember, this is the limit as t goes down to 0 of 1 over t times Qt minus the identity. That is a limit in the Banach space of bounded operators on the bounded functions over S. Under this continuity assumption, this limit exists, and in fact it defines a bounded operator A. Since it forms a bounded operator, that means that we can take the exponential of that operator, and in fact the original semigroup is exactly this power series expansion of that exponential, which converges uniformly in operator norm, since it's given by a nice power series and all of those power series terms are available to us. It's infinitely differentiable and has all the nice properties we could hope for. In particular, we have that Qt satisfies these differential equations we alluded to before, and now I'll give them a name. These are the Komogorov forward and backward equations. This is the forward equation, and this is the backward equation. Now, in this case, there's no difference between them because qt is just given by this exponential, and a commutes with e to the ta, so you can write it on either side with no problem. But it's important to note that in some cases that we may have time to explore much later in this course, one of these equations might make sense, but the other not. For example, suppose that we had an operator A that was not a bounded operator. An operator A which eats bounded functions and spits out functions that aren't necessarily bounded. Well, then this doesn't even make sense, because if I try to apply qt to any operator in its domain, that's going to be a bounded function. But on this side, A applied to that function won't be bounded, and I can't apply qt to that unbounded function anymore. On the other hand, this could make sense. Qt will be applied to a bounded function on both sides, and now what we're saying is that the result might be an unbounded function over here, or when you differentiate the action of t. Now, if A is a bounded operator, it's easy to see that these equations with this initial condition have this as the unique solution. After all, linear ODEs like this always have unique solutions determined by their initial conditions, and it's an easy thing to check that this power series is the solution of these ODEs. So that's on the menu for next time, proving that if we have operator continuity for the semigroup at time 0, then it's as nice as it could possibly be and has a bounded generator so that the semigroup is given by this exponential. That'll give us many tools to explore the action of that semigroup and the behavior of the associated Markov process.